Now in this lecture we'll answer two questions. In the first question we find out the size of this angle x, and in the second question we find out the area of the green shape. So we start with the first question. In the drawing we have a quarter circle, AOB is a quarter circle, therefore this angle AOB is a right angle. In addition we know that angle APQ, this angle is also a right angle. We also know that AP equals to PQ, and our task is to find out the size of angle PQB. This is equal to x. We have to find out the value of x, of angle x. So first of all, we complete this quarter circle to a semicircle. We define this point M. So actually, line segment AM is the diameter of this semicircle according to our construction. Because we completed the quarter circle to a semicircle, therefore OM is the diameter of the semicircle. So I write now AM is the diameter of the semicircle. AM is the diameter of the semicircle. AM is a diameter, it is absolutely straight line. So if we focus on the right side of the straight line AM, at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AM at point O? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we extend PQ, line segment PQ, by a straight line until it touches the semicircle. But the question is, well, the extended line segment PQ will touch the semicircle. We'll assume that the extended line segment PQ will touch the semicircle at this point. We define the touching point of the extended line segment PQ with the semicircle. This point is point L. And it is given in the question that peripheral angle A, that angle AB equals to angle APQ equals to 90 degrees in its size. So we extended the straight line PQ, and according to our assumption, the extended line segment PQ touches the semicircle at this point, point L. So, actually, peripheral angle APL subtend on AL, that is the diameter, that is peripheral angle APL subtend on AL, because the touching point of the extended PQ with this semicircle is at this point, point L. So we have here actually created peripheral angle APL that subtend on AL and this is a contradiction to rule 5. Because according to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the moment we have a circle, this is peripheral angle A or B that is equal to 90 degrees inside. Therefore, according to this rule 5, peripheral angle A or B must subtend on the diameter of the circle. Therefore, AB must be the diameter of this circle. So here we have peripheral angle APL that is equal to 90 degrees inside according to what is given in the question, and peripheral angle APL subtend on AL that is definitely not the diameter of the semicircle. Why AL is not the diameter of the semicircle? Because AL, chord AL, doesn't pass through point O, that is the center of the semicircle, and we know that only a chord that passes through the center of the circle or semicircle can be the diameter of the semicircle. AL doesn't pass through point O, therefore AL is not the diameter of the semicircle. This is a contradiction to rule 5 because peripheral angle APL is right angle. Therefore, peripheral angle APL must subtend on the diameter of the semicircle, but AL is not the diameter of the semicircle. So this is a contradiction to rule 5. Therefore, we cancel this option. This is to say the extended line segment PQ doesn't touch the semicircle at point L, because it is a contradiction to rule 5. Okay. So in the next step, we'll assume that the extended line segment PQ will touch the circle at this point that we will define as point H. So we have here peripheral angle APH that subtend on AH. Again, peripheral angle APH subtend on AH. But AH is definitely not the diameter of the semicircle. Why AH is not the diameter of the semicircle? Because AH doesn't pass for point O. And because of the fact that AH doesn't pass through point O, that is the center of the semicircle, AH cannot be the diameter of the semicircle. Therefore, it is a contradiction to rule 5, because we have peripheral angle APM that is equal to 90 degrees in size. So it must subtend on the diameter of the semicircle, but actually it is subtend on AH that is not the diameter of the semicircle. So this is a contradiction to rule 5. Therefore, from those two contradictions, we will arrive to the conclusion that the extended side PQ will touch the semicircle at this point, point M, and not in any other point. Otherwise, we will have contradiction to rule 5. So the extended line segment PQ must touch the semicircle at point M and not in any other point. Now, we don't have any contradiction to rule 5. Why? Because we have peripheral angle APL, that is a right angle, and peripheral angle APL subtend on AM, that is the diameter of the semicircle. According to our construction, AM is the diameter of the semicircle. Exactly according to rule 5. I repeat again, we have peripheral angle APM that is equal to 90 degrees in its size, and indeed it subtend on AM, that is the diameter of the semicircle according to rule 5. Okay. In the next step, We join points A and Q together by a straight line. By joining points A and Q, we can get the right and associated triangle, triangle APQ. Triangle APQ is an associated triangle because angle APQ is right angle, and triangle APQ is also, again, triangle APQ is a right angle because angle APQ equals to 90 degrees in size, and triangle APQ is also an associated triangle because side AP equals to side PQ. And we have the rule that in front of equal sides in a triangle there are equal angles. So if you relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. This is true in any triangle, and therefore it is true in triangle APQ. So which angles we have in triangle APQ? In the right triangle, triangle APQ, we have this angle that is a right angle, plus alpha, plus 2 alpha, that is to say plus 2 alpha. In total, the sum of those two angles must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees in its size. Here we divide this equation by 2, and finally we get that the size of angle alpha is 90 degrees over 2, that is 45 degrees. So actually this is angle alpha, the size of this angle alpha is 45 degrees. Likewise, the size of this angle alpha is 45 degrees. In the next step, we'll prove that the right triangle AOQ, the right upper triangle AOQ, can go into the lower right triangle OQM according to side angle side rule. So why those two right triangles can go into each other? We prove that the upper right triangle AOQ can go into the lower right triangle, triangle OQM, according to side angle side rule. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOQ is equal to side OM of the right triangle OQM. Why? Because they're both the area of the semicircle, therefore they are equal to each other. So AO equals to OM, AO equals to OM equals to the radius of the semicircle. In addition, those two angles are both right angles, therefore they are equal to each other. So angle AOQ in the right triangle AOQ is equal to this angle, angle MOQ, on the right triangle OQM. And again, we can find out that angle AOQ in the right triangle AOQ equals to angle MOQ in the right triangle OQM. They are both equal to 90 degrees, therefore they are equal to each other. And finally, this is side OQ, that is the common side that belongs to both triangles. So we can find out that OQ equals to itself as a common side that belongs to both triangles. So OQ equals to OQ is a common side that belongs to both triangles. So if you prove that those two right angles can go into each other according to side angle side rule. So already know. You actually prove that the right upper triangle A or Q congruent, this is the sign of congruent, to the right lower triangle, triangle OQM, according to side angle side rule. That is to say, that we prove that those two sides and the angle that is included between those two sides in the upper right triangle A or Q corresponding equal to those two sides and the angle that is included between those two sides of the right lower triangle, triangle OQM. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, actually AO is the radius of the semicircle that we define as R, and OM is also the radius of the semicircle that is equal to R. So from the fact that those two right triangles can go into each other, we derive that the following, we derive that side AQ on the right triangle AOQ is equal to side QM on the right triangle OQM. And again, from the fact that those two right triangles can go into each other, we derive that side AQ of the right upper triangle AOQ is equal to side QM of the right lower triangle triangle OQM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other on their lengths. So if you found out that side AQ is equal to side QM. So if we focus on the big triangle AQM, we have the rule that says that in front of equal sides in the triangle there are equal angles. So in the big triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So in the drawing we have triangle ABC that could be any triangle. The three angles alpha, beta and gamma are defined as an interior angles because they are located inside triangle ABC, while this is angle ACQ is equals to E. This angle ACQ is equals to E is defined as an exterior angle because of the fact that it is located outside triangle ABC. And according to this rule 8, the size of this exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is angle gamma. This is an interior angle that definitely adjacent to angle E. The two other interior angles that are not adjacent to angle E are those two angles alpha and beta. So therefore the size of this angle E equals to alpha plus beta, that is the size of the two interior angles that are not adjacent to angle E. So in conclusion, if we found out that the size of angle E is equal to alpha plus beta, that is the size of the two angles that are not adjacent to angle E. So angle E equals to alpha plus beta. So we can actually implement rule 8 in our drawing. Well, because in our drawing, we have, if we focus on the big triangle AQM, actually it is associated with triangle AQM because side AQ equals to side QM. In the big triangle AQM, angle X, this is angle, this angle is angle PQO, that is defined as an external angle of the associated triangle AQM. And according to rule 8, the size of this external angle PQM is equal to the sum of the two angles that are not adjacent to it. This is angle AQM that is definitely adjacent to this angle AQP. The two other angles that are not adjacent to it are those two angles, beta and beta. And therefore the size of the angle AQP is equal to beta plus beta, according to rule 8. So the size of the angle AQP is equal to the sum of the two angles that are not adjacent to it. That is to say, it is beta plus beta. Beta plus beta, that is 2 beta. So if you found out that the size of the triangle AQP is equal to 2 beta. But we have already found out that the size of angle AQP is 45 degrees. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2b. Here we will divide this equation by 2 and find out that angle beta, the size of angle beta is equal to 45 over 2, that is 22.5 degrees. So here, the size of this angle beta is equal to 22.5 degrees. And the size of this angle beta is also equal to 22.5 degrees. We also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in this right triangle OQM must be equal to 180 degrees. So which angles we have in the right triangle OQM? You have this angle that is a right angle, plus this angle that is equal to angle beta equals to 22.5 degrees in its size, plus this missing angle, that is angle OQM. So in total, the sum of those two angles must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So repeat again. The sum of the angles in the right triangle OQM must be equal to 180 degrees. So which angles we have? The sum of those three angles must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 180 degrees minus 90 degrees is 90 degrees, and it is equal to 22.5 degrees plus the size of the missing angle OQM. So 22.5 degrees plus the size of the missing angle OQM is equal to 90 degrees. Here we subtract 22.5 degrees from this equation, and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So if you found out that the size of the missing angle OQM is 67.5 degrees. We have the rule that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles, and vertex angles are equal to each other, so angle alpha equals to angle beta. Those two angles 1 and 2, they are also defined as vertex angles, and vertex angles are equal to each other. So angle 1 equals to angle 2. Those two angles are also defined as vertex angles, and vertex angles are equal to each other. So x equals to 67.5 degrees. Again, x equals to 67.5 degrees. According to the rule, it said that vertex angles are equal to each other. Get that angle x equals to 67.5 degrees because those two angles are defined as vertex angles and are equal to each other on their sides. So angle x equals to 67.5 degrees in its size, and that is the answer to the question. That is to say, if we found out that angle x, the missing angle x is equal to 67.5 degrees in its size. So we finish the first question. In the next step, I present to you the second question, and we will solve the second question of this lecture. In the second question, our task was to find out the area of this grand shape. So in the drawing, we have a big semicircle. PQ equals to 10, that is to say the diameter of this semicircle equals to 10 units in its length. Therefore, the radius must be equal to 10 over 2, that is 5. The radius of this semicircle must be equal to 5 units in its length, because it is half the diameter. The radius of the semicircle is equal to 5 units in its length. In addition, it is given us the question that inside this big semicircle we have two squares. We have the big square ABCD and we have the small square MEFC. And our task is to find out the area of this grand shape. Okay, so first of all, we define the center of this semicircle. This point is point O. We define the length of line segment OC as x. We define one side of this square ABCD as A. That is to say, one side of square ABCD equals to A units in its length according to our definition. So AB equals to AD equals to DC equals to CB equals to A, because all the sides of any square are equal to each other in their lengths. So BC also equals to A. BC equals to A. So what is the length of BO? BO equals to BC minus OC. Again, BO equals to BC minus OC. So I write it down. The length of the missing side BO is equal to BC minus OC. BO equals to BC. BC is A. Minus OC. OC is X according to our definition. So in total, we have found out that BO equals to A minus X units in its length. BO equals to A minus X units in its length. In the next step, we define one side of the small square MEFC as B. So MC equals to B units in its length according to our definition. CF also equals to B. In the next step, we join points O and A together by a straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle that is equal to 5 units in its length. Likewise, we will join points O and A together by a straight line. OE is of course also the radius of this semicircle that is equal to 5 units in its length. MEFC is the square, and we know that all the angles inside any square are right angles. Therefore, this angle is a right angle. Likewise, ABCD is a square, and therefore this angle ABC must be equal to 90 degrees in its side. So here we get two right angles, the right angle ABO and the right angle EFO, those two right angles. So in the next step, we implement the Pythagoras theorem on those two right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So we copy the right angle ABO in a new page, we will implement the Pythagoras theorem on this right angle, triangle ABO. Side AB equals to A units in its length. We have already found out that side BO equals to A minus X units in its length. And the hypotenuse AO equals to 5 units in its length because it is the radius of the semicircle. So AO equals to 5. So here by PT is the equation for Pythagoras theorem. So actually, this is the right triangle ABO that comes from the original drawing. This right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I write it down. AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equal to AB squared. AB is A, therefore AB squared is A squared plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. And so we found out that according to equation 1, 25 equals to A squared plus A minus X squared. Likewise, I copy the right triangle EOF in a new page and implement the Pythagoras theorem on this right triangle EOF. Here by PT is the abbreviation for Pythagoras theorem. Side OF equals to X plus B units in its length. The hypotenuse O equals to 5 units in its length. And side EF equals to B units in its length because it is one side of the small square AMEFC. So actually, this is the right triangle ECF that are coming from the original domain. According to the Pythagoras theorem, in this line diagram, ECF, CE squared, that is the square of the hypotenuse, equals to EF squared plus FC squared. But again, CE squared equals to EF squared plus CF squared. So I write it down. This will be equation 2. According to equation 2, CE squared, that is the square of the hypotenuse, is equal to EF squared plus CF squared. The hypotenuse C equals to 500 units now, therefore CE squared is 5 squared, that is 25. And it is equal to EF squared. EF is B, therefore EF squared is B squared plus CF squared. CF is X plus B, therefore CF squared is X plus B squared. So in total, according to equation 2, we found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, while according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. In the next step, we will create equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. So according to equation 3, according to equation 1 must be equal to 25 according to equation 2. According to equation 1 equals to A squared plus A minus X squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So in total, according to equation 3, we have found out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we will open the brackets on both sides of this equation, equation 3, and we get that according to equation 3, A squared plus A minus X squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X. And it is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation 3, so X squared will get cancelled. So in this side of the equation 3, we have left with A squared plus A squared, that is 2A squared minus 2AX equals to B squared plus B squared is 2B squared plus 2XB. According to equation 3, we found out that 2A squared minus 2AX equals to 2B squared plus 2XB. Here we will divide this equation 3 by 2, and we get that 2A squared over 2 is A squared, minus 2AX over 2 is minus AX, and this equals to 2B squared over 2 is B squared, plus 2AXB over 2 is XB. So in total, if we found out that according to equation 3, A squared plus AX equals to B squared plus XB. Here we will add AX to this equation 3, and we get that according to equation 3, A squared equals to AX plus XB plus B squared. Here we subtract B squared from this equation 3, and when we get that a square minus b square equals to ax plus bx. According to the familiar algebraic identity, a square minus b square equals to a plus b times a minus b, and it is equals to ax plus bx. Here we take out x as a common factor from those two expressions, so inside the brackets we left with a plus b. Okay, so in total, according to equation 3, we found out that a plus b times a minus b equals to x times a plus b. Here we will divide this equation 3 by a plus b. Actually, it is allowable to divide the equation by a plus b because a plus b can never be equal to 0. Because a is the length of the one side of the big square ABCD, and b is the length of one side of the small square MEFC. So both a and b, they are both positive numbers, and when you add two positive numbers to each other, the result must be a positive number. So a plus b is a positive number, and therefore we can divide the equation 3 by a plus b. So a plus b times a minus b over a plus b is a minus b. And it is equal to x times a plus b over a plus b is x. So in total, according to equation 3, we actually found out that a minus b equals to x. Here we will add to this equation 3b, and we get that according to equation 3, a equals to b plus x. Here we subtract from this equation 3 x, and we get that according to equation 3, a minus x equals to b. A minus x equals to b according to equation 3. And a minus b equals to x. Our task is to find out the area of this green shape. So what is the area of the green shape? So actually, from the drawing, it is very easy to see that the area of the green shape is equal to the area of the semicircle minus the area of the big square ABCD minus the area of the small square MEFC. So repeat again, we found out that the area of this green shape the area of the green shape equals to the area of the semicircle minus the area of the big square ABCD minus the area of the small square MEFC. We already found out that the radius of this semicircle is 5. Actually, the area of any semicircle is the area of the circle over 2. That is to say, it is pi r square over 2. So the area of the semicircle is pi r square over 2. minus the area of the big square ABCD. We know that one side of square ABCD equals to A units in its left, therefore the area of any square is equals to one side squared. Therefore the area of this square ABCD is A squared, so it is minus A squared, minus the area of the small square. One side of the small square is equal to B units in its left, therefore the area of the small square is B squared. So it is minus B squared. So in total we found out that the area of the green shape equals to pi r square over 2 minus A square minus B square. We already found out that the radius of this semicircle r equals to 5. Therefore pi r square over 2 is pi 5 square over 2, that is 25 pi over 2. So the area of this semicircle equals to 25 pi over 2 square units in its size minus A square minus B square. So here we take out minus 1 as a common factor from those two expressions. So inside the brackets we will have A square plus B square. So if you found out that the area of the green shape in total equals to the area of the semicircle, that is 25 pi over 2 minus A square plus B square. We have already found out that according to equation 1, according to equation 1, (25) equals to A square plus A minus X square. Repeat again, according to equation 1, we have already found out that 25 equals to A square plus A minus X square. We have already found out that A minus X equals to B. If A minus X equals to B, it means that A minus X square must be equal to B square. A minus X square equals to B square. So in equation 1 we have 25 equals to A square plus A minus X square. And we just like to find out that A minus X square equals to B square. So we substitute A minus X square in this equation 1 by B square. And we get that according to equation 1, 25 equals to A square plus A minus X square, that is B square. So today we found out that according to equation 1, 25 equals to A square plus B square. Therefore, we can substitute A square plus B square in this equation by 25. And we get that the area of the green shape in total equals to 25 pi over 2, that is the area of the semicircle, minus A square plus B square. But A square plus B square is 25. So we substitute A square plus B square by 25. So if you found out in total the area of the green shape equals to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the value of this expression 25 pi over 2 minus 25 is equal to 14.27 square units. So repeat again, if you found out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units. In terms of numbers, the area of this green shape equals to 14.27 square units in its size. Okay, so we finished with the second question. In the next step, I'll summarize the lecture. We start with the first question, of course. Our task in the first question is to find out the size of this angle, angle x. So the size of angle PQB is equal to x degrees in its size. We have to find out the value of angle x. So in the drawing we have a quarter circle. AOB is a quarter circle, and therefore this angle equals to 90 degrees. In addition, we know that this angle APQ, that is also a right angle, and we also know that Inside this quarter circle, we have side AP equals to side PQ. Again, our task is to find out the size of this angle X. So first of all, we completed the quarter circle to a semicircle. We completed this quarter circle AOB to a semicircle, and we find this point as point M. So actually, this is a semicircle, and therefore AM is the diameter of the semicircle according to our construction. Again, because of the fact that we created from the quarter circle a semicircle, AM must be the diameter of the semicircle. AM is the diameter of the semicircle according to our construction. So AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its side. In the next step, we extended 97 PQ by straight line until it touches the semicircle. The question now is where the extended 97 PQ will touch the semicircle. We will assume that the extended 97 PQ will touch the semicircle at this point, point A. Okay? So, we have peripheral angle APL, that according to what is given as the question, peripheral angle APL equals to peripheral angle APL equals to 90 degrees in size, and peripheral angle APL subtend on AL. But AL is definitely not the diameter of the semicircle, because AL doesn't pass through point O, that is the center of the semicircle. And we know that the diameter must pass through the center of the semicircle. AL doesn't pass through the center of the semicircle, therefore AL is not the diameter of the semicircle. Therefore we have contradiction to rule 5. Because we have peripheral angle APL that is equal to 90 degrees in its side according to what is given in this question. So peripheral angle APL must subtend on the diameter of the semicircle, but AL is not, it subtends on AL, that is not the diameter of the semicircle. So we have contradiction to rule 5. Therefore, the extended side PQ cannot touch the semicircle at this point, point A. Now we'll check the other option that we have. That the extended side PQ will touch the semicircle at this point, point H. So we get that peripheral angle APH, that is equal to 90 degrees in size, and peripheral angle APH subtend on AH. But AH is definitely not the diameter of the semicircle, because AH doesn't pass through point O. AH definitely doesn't pass through point O, that is the center of the semicircle. So any chord that doesn't pass through the center of the semicircle cannot be the diameter of the semicircle. So AH is not the diameter of the semicircle, therefore we have a contradiction to rule 5. Because we have peripheral angle APH that is equal to 90 degrees in size, and still it doesn't subtend on the diameter of the semicircle, because AH is not the diameter of the semicircle. So due to those contradictions, we must conclude that the extended side PQ must touch the semicircle at point M and not in any other point. Otherwise, we will have contradiction to rule 5. Now, we don't have contradiction to rule 5 anymore, because peripheral angle APM is equal to 90 degrees in size, and indeed peripheral angle APM subtend on AM, that is the diameter of this semicircle, exactly according to rule 5. Okay, so in the next step, we join points A and Q together by straight line. By joining points A and Q, we get triangle AQP. This is actually a right and associated triangle. We know that the sum of the angles in a triangle must equal to 180 degrees. It's given in the question that PQ equals to PA. So in that triangle APQ, in front of those two sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. So in that angle APQ, the sum of the angles must be equal to 180 degrees. So which angles we have with the right angle APQ? We have this angle that is right angle, that is to say it is equal to 90 degrees in size, plus alpha, this is 2 alpha. In total, the sum of those three angles must be equal to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtracted 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So this is angle alpha, that is equal to 45 degrees in size, and this is also angle alpha, that is equal to 45 degrees in its size. In the next step, we prove that those two right angles can go into each other according to side angle side rule. That is to say, the upper right angle AQO can go into the lower right angle triangle OQM. So why those two right angles can go into each other? First of all, side AO of that triangle AOQ is equal to side OM of that triangle OQM. They're both the area of the circle, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, OQ is a common side that belongs to both angles. So I can write down that OQ equals to itself is a common side that belongs to both angles. So I can prove that those two right angles can go into each other according to side angle side rule. That is to say, those two sides and the angle that is included between those two sides in the right upper triangle AUQ corresponding equal to those two sides and the angle that is included between those two sides in the lower right triangle OQM. And therefore those two right angles can go into each other according to side angle side rule. So if we found out that the right upper triangle AUQ can go in, this is the side of framework, to the right lower triangle OQM according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive the side AQ of the right triangle AQO is equal to side QM of the right triangle OQM. We derive the side AQ equals to side OM according to the rule. Side AQ equals to side QM. Side AQ equals to side QM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So AQ equals to QM. So in the big triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other. So in the next step, I actually presented to you rule 8, and we implemented rule 8 in our drawing. So, a bit quickly on rule 8. According to rule 8, an external angle of a triangle is equal to the sum of the two angles that are not adjacent to it. So in the drawing we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as interrogants because they are located inside triangle ABC. Well, this is angle E, angle AC equals to E. It is defined as an external angle because it is located outside triangle ABC. And according to this rule 8, the size of this interrogant E is equal to the sum of the two interrogants that are not adjacent to it. Angle gamma is definitely adjacent to angle E. The two other interrogants that are not adjacent to angle E are alpha and beta. So angle E equals to alpha plus beta according to this rule 8. So alpha plus beta equals to E. So we can implement rule 8 in our drawing. Well, if you focus on the big triangle AQM, in the big triangle AQM, this is angle AQP, is equals to 45 degrees inside. This angle AQP is defined as an external angle in relation to the big triangle AQM. So the size of this external angle AQP must be equal to the sum of the two angles that are not adjacent to it. This angle AQM is definitely adjacent to angle AQP. The two other angles that are not adjacent to it of those two angles, beta and beta. So the size of the angle AQP must be equal to beta plus beta according to rule 10, to rule 8. And again, according to rule 8, if you relate to the big triangle AQM, if you relate to the big triangle AQM, according to rule 8, the size of the external angle AQP, the size of this external angle AQP equals to beta plus beta. The size of the external angle AQP equals to beta plus beta, this is 2 beta. So the size of the big of the external angle AQP equals to 2 beta. But we have already found out that the size of the external angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. And we get that 45 degrees equals to 2 beta. Here we divided this equation by 2 and found out that angle beta equals to 45 degrees over 2, that is 22.5 degrees in its size. So this is angle beta, that is equals to 22.5 degrees, and this is also angle beta, that is equals to 22.5 degrees in its size. We also know that the sum of the angles in any triangle is equal to 180 degrees. So if we relate to the lower triangle, the lower right triangle QOM, the sum of the angles of this lower triangle OQM must be equal to 180 degrees. 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is 90 degrees, plus this angle that is 22.5 degrees, plus this missing angle OQM. In total, the sum of those two angles must be equal to 180 degrees. Repeat again, the right triangle OQM. 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, in total must be equal to 180 degrees. So here we subtract 90 degrees from this equation and finally found out that 180 degrees minus 90 degrees it is 90 degrees, and 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtract 22.5 degrees from this equation and finally found out that the missing angle OQM, this is the missing angle OQM, that equals to 90 degrees minus 90 degrees minus 22.5 degrees is 67.5 degrees. So the size of this missing angle OQM is equal to 67.5 degrees in its size. Now we use the rule that says that vertex angles are equal to each other. Those two angles are defined as vertex angles, and therefore they are equal to each other. That is to say, angle alpha equals to angle beta. Those two angles are also defined as vertex angles, and they are equal to each other. That is to say, angle 1 equals to angle 2. So we can implement the rule in our drawing, because in our drawing we have those two vertex angles that must be equal to each other and their sizes. So if we found out that angle x equals to 67.5 degrees in size. And again, if we found out the size of this angle x, that is the angle that we are looking for in this question, is equal to 67.5 degrees in size. Again, according to the rule, the vertex angles are equal to each other. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So, in the drawing, we have a semicircle. We know that PQ equals to 10. That is to say, the diameter of this semicircle equals to 10 units, and therefore the radius must be equal to 5. Okay. In addition, we know that inside this semicircle we have the big square ABCD and the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equal to 5 units in itself. Likewise, to join points O and D together by straight line, OE is also the radius of the semicircle that is equal to 5 units in its length. In the next step, we define one side of the big square ABCD as A, and we define one side of this small square MEFC as B. So AB equals to BC equals to CD equals to DA equals to A. What is the length of the, we defined the length of line segment OC as X. So what is the length of BO? BO equals to, must be equal to BC minus OC. Again, BO equals to BC minus OC. Because again, BO equals to BC minus OC. BC is A according to our definition, minus OC. OC is X also according to our definition. So in total, we found out that BO equals to A minus X units in its length. Likewise, OF equals to X plus B, EF equals to B, and EO equals to 5 units, because it is the radius of the semicircle that is equals to 5 units in its length. In the next step, I copied the right triangle ABO in the new page and we implemented the Pythagoras theorem on the right triangle ABO. So see, this is the right triangle ABO, this is the commit from the original domain. According to the Pythagoras theorem, linear right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle AOB is AO, therefore the square of the hypotenuse is AO square, and AO square must be equal to AB square plus BO square. AO is 5, therefore AO square is 5 square, this is 25, and it is equal to AB square. AB is A, therefore AB square is A square, plus BO square. BO is A minus X, therefore BO square is A minus X square. So in total, according to equation 1, we have found out that 25 equals to A square plus A minus X square. This is according to equation 1. So in the next step, I copied the right triangle EOF here in the new page and implemented the Pythagoras theorem, this right triangle and EOF. So okay, this is the right triangle EOF. This is the right triangle EOF, this is copied from the original domain. So in this right EOF, according to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, equals to EF square plus OF square. Again, OF square equals to EF square plus OF square. OF is 5, therefore OF square is 5 squared, that is 25, and it is equals to EF square. EF is B, therefore EF square is B square, plus OF square. OF is X plus B, therefore OF square is X plus B square. So in total, according to equation 2, we found out that 25 equals to B square plus X plus B square. In the next step, we created equation 3 that says that 25 according to equation 1, 25 according to equation 1 must be equal to 25 according to equation 2. And again, according to equation 3, we found out that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A square plus A minus X square. And it is equals to, it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B square plus X plus B square. And then according to equation 3, we found out that A square plus A minus X square equals to B square plus X plus B square. Here we open the brackets on both sides of this equation and equation 3, and finally found out that A square plus A minus X square. A minus X square equals to A square plus X square minus 2A minus 2 times A times X. And it is equals to B square plus X plus B square. X plus B square equals to B square plus X square plus 2 times X times B. So here we have X square on both sides of this equation, so X square will get cancelled. After we cancelled X square in this side of equation 3, we left only with A square plus A square, that is 2A square, minus 2XB, minus 2AX. And the other side of equation 3, we have B square plus B square, that is 2B square, plus 2XB. Here we added 2XB to this equation. We added 2, here we divided this equation equation 3 by 2, and finally found out that 2a squared over 2 is a squared, 2ax over 2 minus 2ax over 2 is minus ax, 2b squared over 2 is b squared, and 2xb over 2 is bx. So total we found out that a squared minus ax equals to b squared plus bx. Here we added ax to this equation 3, and finally found out that a squared equals to ax plus xb plus b squared. Here we subtracted b squared from this equation 3, and finally found out that a squared minus b squared equals to ax plus xb. We have the famous algebraic identity that a squared minus b squared equals to a plus b times a minus b. Here we have ax plus bx. Here we took out x as a common factor from those two expressions, so inside the brackets we left only a plus b. And we found out that a plus b times a minus b equals to x plus x times a plus b. Again, a plus b times a minus b equals to x times a plus b. Here we divided this equation 3 by a plus b. Because of the fact that a and b are lengths, a plus b can never be equal to 0. Therefore it is allowable to divide this equation 3 by a plus b. So we divided the equation 3 by a plus b. So here a plus b will get cancelled, and we have to only with a minus b. Here also a plus b will get cancelled, and we have to only with x. So according to equation 3, we found out that a minus b equals to x. Here we added b to this equation, and found out that a equals to x plus b. Here we subtracted x from this equation in equation 3, and finally found out that a minus x equals to b. If a minus x equals to b, it means that a minus x squared must be equal to b squared. Okay. Our task is to find out the area of this green shape. From the moment it is very easy to see that the area of the green shape equals to the area of the semicircle minus the area of these squares. And again, the area of the green shape must be equal to the area of the semicircle minus the area of the big square minus the area of the small square. What is the area of the semicircle? Actually, note that the area of any semicircle equals to the area of the circle over 2. That is to say, it is pi r square over 2. Minus the area of the big square. One side of the big square equals to a. Therefore, the area of this big square must be equal to a square. Minus the area of the small square. One side of the small square is equal to b. Therefore, the area of the small square must be equal to b square. So in total, we found out that the area of the green shape equals to pi r square minus a square minus b square. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi over 2. Here we took minus 1 as a common, we took out minus 1 as a common factor from those two expressions, so inside the brackets we left with a squared plus b squared. So here, according to equation 1, 25 equals to a squared plus a minus x squared. But we have already found out that a minus x squared equals to b squared. Therefore, we substitute a minus x squared here by b squared. We substitute a minus x squared here by b squared. So according to equation 1, we found out that a squared plus b squared equals to 25. So we can substitute a squared plus b squared here by 25. We did it, and we found out that in total the area of the green shape equals to 25 pi over 2, and minus a squared plus b squared is 25. So in total we found out that the area of the green shape equals to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the area of the green shape equals to 14.27 square units in its size. Okay, thank you very much.